Dear dignitaries, dear presidents, rectors, dear colleagues, dear friends, dear everybody who is in this audience, it's an enormous pleasure and honor for me to be here and to be able to give you this final lecture of the fantastic World Symposium on Copernicus. What a week it has been. It was already said during the various speeches. We've seen and heard everything. We have heard astronomy, we've heard about history, we've heard about philosophy, culture, religion, anthropology. So much was really happening, centered around the theme of Copernicus. And what I hope to do today is sort of take that a little bit further, also towards the future. The enormous revolution that Copernicus basically started 5 centuries ago in changing our view of the world, that's still continuing. And it's continuing thanks to the wonderful new telescopes that we have, of which James Webb Space Telescope is just one example. But before we do that, let's actually take a step backwards. Astronomy. It was already said, astronomy is actually a very inclusive topic. Because viewing the night sky, as you can do here, see here on this picture with the Warsaw telescope, is actually available to everyone, everywhere on the world. And even in COVID times, with social distancing, always we had the sky that we could look at and give us inspiration. And if you just look at the sky, then immediately you have to start to wonder, you know, where do we actually come from? What is our place in this gigantic universe? And of course, Copernicus studied that and was fascinated by that. But just as much, the young children here in Toruń, in Poland, elsewhere on the world, are fascinated by looking at the night sky, and they get actually inspiration from there. Now, I'm actually standing here also as past president of the International Astronomical Union. That is the worldwide organization of all professional astronomers, some 12,000 astronomers worldwide of more than 100 countries. And Poland has been one of the earliest members. In 1922, it joined already, just 3 years after the foundation of the International Astronomical Union. And Poland and the IAU and Copernicus have actually gone hand in hand over this past century. Once every 3 years we have our General Assembly, and you see that there was an extraordinary General Assembly in 1973, especially to commemorate 500 years of Copernicus. There are symposia in Poland under the IAU premises. Here you see one dedicated to planetary systems like our own solar system with Copernicus. But just last week there was another IAU symposium on planetary nebulae actually happening in Krakow. The executive committee of the IAU has 6 vice presidents, but it was not until 1973 until we had our first female vice president. And that was actually Wilhelmina Iwanowska, who was actually professor here at the university in Toruń. And another connection between the IAU and Poland is certainly the outreach and the education, which are so central of also the Polish Astronomical Society and of magazines like Urania and Science Now Studios that produce wonderful exhibitions and that are an inspiration to many people. Another function of the IAU is actually the naming of objects. And I actually looked it up. This is where Copernicus, the asteroid 1322, is today. It's just touching the orbit of Mars, actually. You see that Copernicus is actually a bit eccentric asteroid. It's having a very unusual orbit. But this is actually the asteroid that was named by the IAU after Copernicus. There's also a lunar crater named after Copernicus. And then there is actually a whole star, that's the system 55 Cancri A, that is named after Copernicus. So Poland and worldwide astronomy go actually hand in hand, not just through the IAU, but also through the European Astronomical Society. In 2023 it had its major meeting actually in Krakow. You've heard already during the opening that Poland is member of these big international organizations for putting the biggest telescopes on the ground and in space, the European Southern Observatory and ESA. And there are some fantastic Polish astronomers. I had the pleasure myself to know Bogdan Paczynski when he was in Princeton at the time, the father of Ogel, the talk that you heard from Udalski on the opening day. And of course, the wonderful work by Wolczan on the detection of the first exoplanet around the pulsar. So, Copernicus changed our world views then, some 500 years ago. And this particular diagram has been debated a lot, also in the historical section that I had the pleasure to attend over the last few days. But one of my hobbies is actually astronomy and art. And this is one of two paintings that we actually print that we have at home, about 2 centuries old. And it shows the Copernican system in relation to the Ptolemaic and the Tychonic views of the world. A wonderful print. But even more relevant is this particular print that's hanging right next to it in our house. And this is called the Universal Solar System. And remember, this is made 2 centuries ago, well before the first planet outside our solar system was detected. But here, this artist was already speculating that you have here in the center our own solar system, as it was known at that time, with some 7 planets then. But he was already speculating that other planetary systems don't need to look at all like our own planetary system. Some have more planets, some have less, some closer in, some further out. And that's, of course, exactly the revolution in astronomy, one of the revolutions in astronomy that is happening at this very moment. So let's look at these changes, how our view of the universe has actually changed dramatically over the last 100 years. 100 years ago, we only knew of the atoms and the molecules. We didn't know that about this dark matter and dark energy that actually make up the bulk of the universe. 100 years ago, we only knew of our own Milky Way as a galaxy. And now we know that the universe is actually teeming with galaxies, and we can see the galaxies down to the very earliest times, just a few 100 million years after the Big Bang. This is exactly the era that the James Webb Space Telescope is now probing. Here we are some 13.8 billion years after the Big Bang. We now know that there are supermassive black holes, not just the stellar black holes, but even supermassive black holes, and also in the center of our Milky Way. And 100 years ago, we had no clue where the elements in our body came from, the oxygen, the carbon, the nitrogen that we are made of. We now know that they are made actually by nuclear fusion in stars, and that they are then expelled in supernova and nova explosions back into the interstellar medium. And of course, 100 years ago, we knew only of 8 planets, and that we are all in our own solar system. And now we know that actually planets are more common than stars in our galaxy. We now know, thanks to the discovery of exoplanets, that they are actually very common, and that every star has, on average, at least 1 planet. But often of a type that we don't have in our own solar system. That's a new view. These planets can be somewhat more like Jupiter, they can be like Saturn, but the bulk of them are actually somewhere in between Earth and Neptune, 10 times the mass of the Earth, a type of planet that we don't have in our own solar system. So this raises immediately the question as to what the composition is, how habitable they are, and really whether there could be life elsewhere in the universe. And sort of directly related to that is also the question, how were we formed, actually, some 4.6 billion years ago, our solar system? How was it actually formed? And we are getting new clues on that from going to asteroids and picking up small pieces of material there and bringing them back to Earth to study in laboratories. Or going to a comet. A comet is not just rock, but rock plus ice. And actually the Rosetta mission landed for the first time in humankind on a comet in 2014. And these are all clues from the leftovers from our own solar system, clues as to what happened in our own early solar system. Now, astronomy and all of these new views that we are getting are actually driven by major facilities in space and on the ground. We want to look every time, we want to look sharper, we want to look more sensitive. That can only happen if we improve our technology and we improve the size of our telescopes. And here are some examples of very famous telescopes like the Hubble, like the European Southern Observatory, and like this telescope with the Atacama Large Millimeter Array, ALMA, that is actually the first worldwide collaboration in astronomy. All of these are multinational, intercontinental collaborations. That's the characteristic. And what is wonderful is that all of them also have open data, open archives that are accessible to anywhere, anybody in the world. So you can also go to the archives of these telescopes and download data and look at them yourselves. So one of these big new facilities, and certainly the biggest at the moment, biggest step that is happening now, is the James Webb Space Telescope that undoubtedly many of you have heard about in the news. It's the new flagship mission from NASA in collaboration with the European Space Agency, ESA, and Canada. The name James Webb is not a scientist, very unusual. Usually a big telescope is named after a famous scientist, like Copernicus. But in this case, it's actually named after the NASA administrator that was responsible for the moon program in the 1960s. So this has been a 30-year journey to get there. What you see here is the launch in the corner, the final stage when Webb was released from the Ariane rocket, and it was a very emotional moment because it took 30 years to get to this point. And it has really a testimony to the thousands of engineers, technicians, managers, and also scientists that made this happen. It's also a mission that is of the kind, a price tag that only the United States can do in collaboration with partners. And so it's really the type of mission that you can do only once per generation. So where is Webb now? Well, Webb is actually 4 times the distance of the Earth to the Moon. So it went well beyond the Moon. It's in the so-called L2, Lagrangian point 2, a point where it's actually very stable, and where the Sun, the Earth, and the Moon, which are sort of the noise, provide the noise on the background, are always on the same side. And you see it travels actually with Earth around the Sun. Now, what makes Webb actually unique? Well, Webb is big. It's 6.5 meters in diameter. That's for a space telescope that is very big. And here you see a one-to-one model there. Another thing that makes it unique is its eyes. Its eyes are not like our eyes. That's what you see here with our own eyes. In the visible radiation, you're all familiar with X-rays. You're all familiar with radio. But actually where Webb looks is in between in the infrared, which is very much obscured, the radiation from space, by our own atmosphere, which is of course full of water and CO2, that blocks the radiation from space. So that's why we have to go to space. Now, on Webb, there are actually 4 instruments, a combination of cameras, like you have in your iPhone, and also spectrometers that can basically unravel the colors and into the colors of the rainbow. And these are very sophisticated spectrographs. They are not just pointing at one position, but they are actually pointing at multiple positions at the same time. And so everything combined, the size, the detectors, the instruments, make that the sensitivities are about a factor of 100 to 1,000 better than earlier instruments. And that means that we surely are going to find surprises if we have that much of discovery space. My own involvement with Webb has been for more than 25 years. I've actually been part of the European consortium that co-built the mid-infrared instrument on James Webb. Now, why actually are we going to the infrared? Well, that is because if they have radiation at very large distances, actually by the time it gets to us, thanks to the Doppler shift, it's actually shifted to the red, and it shifts completely out of the visible range into the infrared. So it's shifted to the red, and that is, means that we can also actually use that sort of as a time machine. Far away basically also means long ago. Why the infrared? That was one reason. The other reason is that we can actually peer very deep actually into these dust clouds and see the birthplaces of galaxies, stars, and planets. And that's exactly what the Webb science is. It's basically going from first lights to new planets. Now, the first image that was released on July 11 last year was of this deepest image of the universe to date. Let me take you through this. This is actually a star. This star image is a diffraction pattern of the telescopes that recognize you immediately that this must be a Webb image. This is a cluster of galaxies that actually amplifies the radiation that comes from behind, so it provides a little bit of a lens effect. It also distorts the images of the distant galaxies a little bit, like you see here in this filament. And so thanks to this sort of lens effect, it means we can look even deeper. And indeed, even this first image, which was not yet that deep, showed already and revealed already galaxies that are more than 13 billion years old, so just a few 100 million years after the Big Bang. And that's indeed a very active topic of discussion as to can we find these very earliest galaxies, very earliest stars. Another recent discovery is the supermassive black holes, which we can see now out to very large distances. Here is one that is existed already just 570 million years after the Big Bang. This is a very recent result from last month. Its mass is only about 1 million solar masses, about comparable with the mass of the supermassive black hole in the center of our own galaxy. So this again raises one of these questions: is how did those supermassive black holes come to be? Star-forming galaxies as well, beautiful star-forming galaxies that we see over here in the phantom galaxies. What is red is basically where star formation is currently occurring. This is where a whole new clusters of stars are being born. And the same you see here, interacting galaxies here in the Cartwheel galaxy, where a burst of star formation is actually taking place at the moment. In the last part of my talk, I would like to focus now on really the other worlds close by. We've seen that Webb already gives us new views of our universe. Now let's look at new views of other worlds. And for that, let's actually go back to the Starry Night. You all recognize this constellation, I hope. Yes, that's Orion. And but few people actually ask the question, what is in between those stars when you look at Orion? Well, our origins actually start in the very, very dilute gas that is actually present between the stars. And here you see the Orion Nebula beautifully. That's where, at the moment, new stars and planets are being born. And you see that also here very nicely in this, by now very famous image of Webb, where you see a part of one of these clouds illuminated by young stars. And here inside this cloud, everything that is a red dot is actually where new stars are forming. Here you see actually a jet coming out of a young star that is trying to push away its surroundings. And here's another one with a nice bow shock that is plunging into the cloud. So these are all young stars in the very earliest stages. The pillars of creation, now in the light of JWST, our MIRI instrument. A little bit of a spooky image it looks. It came out actually around Halloween. But you see here, again, these dots here that are young stars that are being born at this very moment at the tip here of these filaments. And this is a picture that was released just yesterday. It's from our own JWST program, again, of a protostar that has a jet that is plunging into the surroundings and is expelling all of this material. The protostar in the disk we cannot see, that's actually hidden behind the dust. All right, good. So we've gone from very large scales to smaller and smaller scales. And now we go to the smallest scales. Now we go to the scales of our own solar system, the scales of protoplanetary disks that actually form when a star collapses to form a star. These rotating disks of gas and dust, and in which planets can form, and which is, of course, entirely analogy with our own formation of our own solar nebula, as postulated, for example, by Kant. And you see here a young planet actually carving a gap into that disk. It's difficult to see the young planets themselves, but what we can see is definitely these gaps that are carved in these disks. And these disks can now be imaged. This is ALMA imaging. You see here a whole gallery of these planet-forming disks. You see the structure in there. We think that this is actually planet formation in action happening now. And one of the big questions is then, of course, what is then the material out of which these new planets are made? And this is where Webb comes in again, the synergy that we now have between some of these very biggest world-class telescopes. On the one hand, ALMA, that is studying the outer parts of the disks, and on the other hand, the Webb telescope that is actually sensitive to the warm gas in the inner part of disks where terrestrial planets are forming. This is, again, a brand new result released on July 24, where we now use actually JWST in one of these planet-forming disks to look for whether or not there is water here where terrestrial planets are forming. And yes, we did see actually very clearly here the fingerprint of warm water in that inner part of that disk. But sometimes we don't see water, and that's also a surprise. This is another disk where we don't see water, but where we see the fingerprints happening of other molecules, of acetylene, very carbon-rich acetylene, of benzene, quite complex carbonaceous molecules. So that's another puzzle. Why are some disks very water-rich, others are very carbon-rich? What kind of planets do we make out of those? Well, that's the big question. How do we build planets and what sets their composition? Why is our Earth like it is, with some water and some carbon happening there? So by studying these disks, we learn about the history, actually, of also more mature planets. And speaking about mature planets, this is also where Webb is actually shining at the moment. This is one of the earliest detections of water in an exoplanet atmosphere. This is a giant planet. Here we see for the first time a very clear signature of carbon dioxide in those planets. Carbon dioxide, CO2, is very abundant. We see it almost everywhere. And then this is, again, a press release just earlier this week, a few days ago. This was released, the first detection of methane, actually, in a exosolar planet, and especially of a very sort of not so massive planet, a Neptune mass planet, likely having an ocean and an H2 atmosphere. And again, carbon dioxide present as well. So these kinds of excitements are happening daily, as you can see. It has been a very exciting week with all kinds of new discoveries from Webb actually announced. So it's good that my talk is actually at the end of the week and not in the beginning of the week. Good, future new views. Where do we go from here? Copernicus did his observations from Fromberg and from Olsztyn. We are building now sort of our new cathedrals. The extremely large telescopes of the ESO, here you're in an animation scene, but this is the actual construction. Again, a few days ago, you see it actually being put together and progress is clearly being made on its construction. And this telescope will be another fantastic instrument to study this question, are we alone in the universe? So let me end by saying that I hope to have shown you that astronomy and science very exciting results happening on a daily basis. They provide inspiration to astronomers, but also inspiration for others. But even more importantly, they provide us with a perspective of our place in the universe. A little bit of sense also a vulnerability. We are only that tiny little dot in that gigantic universe. It brings us a little bit of modesty in that way, and also tolerance. And I think especially in these challenging times, in these trying times that we have as humankind, it's important to realize that we are all world citizens under the same beautiful sky. Thank you very much.